Okay, so today, I think today is kind of a breather, in a certain sense. I'm going to give you one big, fat, juicy theorem, but there's going to be almost nothing there because it's just kind of tying the room together, so to speak. Tying together some stuff that we kind of already know. So while I am doing my thing, if any questions occur to you, this is kind of a good day for questions. I don't think we're in a super hurry here. I'm going to show you one thing and kind of give you this big theorem. One of the theorems got basically, well, I'll put it next. I got like 13 equivalent conditions in it. But the value of this theorem is it gives you many, many ways to think about this concept of invertibility, kind of tying stuff together, as I said. Theorem. Suppose A so let me emphasize this. So in this theorem, I'm only talking about square matrices in rows and columns, the same number of rows and columns. The following conditions are do you all know what I mean by that? Following or logic equivalent, these statements are all the same. Let me give you an example that you may have seen, something like this. What is an equilateral triangle? Can somebody remind me what that is? All sides of the same way. An equilateral triangle everybody remember that from the old days of geometry. This is what an equilateral triangle is, all about the same thing. Let me ask you this. If I have a triangle and all three sides are the same length, what does that mean about the three angles in the triangle? It's all the same. They're all the same. So if you have any triangle where all three sides are the same length, then all three angles are the same. I agree with that? All three angles are the same. And it works the other way. So if I have all sides of the same length, you told me that all angles are the same. What if I say, I don't know much, but I've got a triangle and all three angles are the same? What do you know? All the sides have to be the same. These are two different statements that are logically equivalent. One of them means the other one means. Can anybody think of a third? I mean, we can go to town on this. You can play games with this. Two of the angles are 60 degrees. That's logically equivalent. Why? Why is that the same thing? Right. So what do the three angles have to add up to? 180. Two of them are 60. So I've got 60, 60, and what's left over? 60. So this is really the same thing as all three angles are the same. So I can go to town and make a logically equivalent statement, right? Now I'm going to do this for matrices here, invertible matrices in particular. So here, all these statements are logically. Number one, A is invertible. And I'm going to put this up here just to remind us what this means. A inverse equals A inverse. A is the adjective. Two. A is row equivalent. Two. Anybody remember what this is? If I do my magic, and let's suppose I do start with my invertible matrix, and I do my row reduced echelon form, I do my magic to it, what do I eventually come up with? That is right, the identity matrix. So the row reduced echelon form for the matrix would be the identity 3. If you have a square matrix, and it's the identity, how many pivots does it have? Yeah, it's got exactly n. It's got one for every row and column. So I'm going to put it this way. A has n pivots. And when I say n pivots, I mean it's got n pivot positions. Or you could also say it's got n pivot columns, right? Because every pivot position is a corresponds to the column at the end. Or A has a pivot in every row or column. Right? By the way, if it's row equivalent to the identity, then it's got n pivots, and if it's got n pivots, it has to be row equivalent to the identity, right? Well, so these are the same. These two are the same. Let's see what others we have here. AX equals 0 has only the trivial solution. This one is very important that A is a square matrix, right? If AX equals 0, if you've got a square matrix that has only the trivial solution, then, well, let's see, why is this the same as invertible? Let's go back to this number of pivots. What does it mean when AX has only the trivial solution? Thank you. There's no free variables, right? And that means that every column has to be a pivot column. That means you have to have n pivots. So it's the same as this. And there, it was, I like the way you said no free variables. That means every column is a pivot column. And since it's square, you don't have to worry about. So that means it's only the trivial solution is good enough to give you invertibility. By the way, some of our new fancier terminology. When you have, so what he said, so if you have only the trivial solution for this matrix here, that means that every column is a pivot column. Does anybody remember what that means about the columns, if they're all pivot columns? With regard to some of our other notions. What does that mean with respect to linear independence dependence?
It's linear independent.
That's right. If all the columns are pivot columns, it's linearly independent. So okay. So we've got that one under wraps. 7. The linear transformation EX equals AX is 1 to 1. So we saw that that's connected to linear independence earlier. Eight. Figure out what's coming here. Okay, so suppose that you have, suppose A has n by n has n pivot columns. It has n pivots, right? Suppose that. So there's a pivot in every column, right? There's also a pivot in every row, right? Everybody agree? Because there's n columns, there's also n rows. So if you got n pivots, there's got to be one in every row. You can't have two pivots in the same row. Agreed? If A has a pivot in every row, what's true about this equation? You can solve it, right? Because that means that the columns of A span Rn. So this is solvable for all B in Rn. And in fact, this is like that statement I gave you for the triangles where I said two of the angles for 60 degrees is good enough, right? This is similar to this. The equation AX equals B is solvable is good enough, but since it's n by n, the solution is also unique. You could also state this: AX equals B has a unique solution for every B in Rn. Can somebody explain why it has to be unique? That's exactly right. That's exactly right. You've got that statement right there means that there must be a pivot in every row, but the matrix has the same number of rows and columns. So there's a pivot in every column. So the columns are linearly independent. So there's only one solution. So there is a solution and it's only one, so it's unique, as a matter of fact. We stated this a moment ago, sort of help us out here. Columns of A span Rn. That's equivalent to that statement there. 10. The linear transformation guess what goes in the blank here. We've already done one that's sort of like this. It's also onto. It's correct. Yeah, and this is kind of a buildup from this because we say the columns span. Sounds like this is onto. Nobody's lonely over an Rn. Okay. And this is one that's a little bit. This is the one I'm going to take apart a little bit later. Number 11. There is a matrix C in R n by n with C A I n. Number 12, there is a matrix D and 13, I guess it's A transpose. So Um. By the way, the 13 is not too bad, because actually we showed 13 is the same thing as this last time. In fact, we showed A is invertible means A transpose invertible, and the inverse of A transpose is the transpose of A inverse. That was one of the last things that we did. We showed that one. Can somebody tell me? There's a subtle difference between these two statements and this. Can anybody see what it is? See, all this one tells me is, okay, I've got my matrix A, right? This just tells me deep in the depths of some Stephen King novel, I can find some other matrix C that hits this on the left-hand side and makes the identity. Why does that mean that there's another matrix D that I can hit on the right side that makes that the identity? And let me show you why this could be trouble. This won't be trouble in our case, otherwise I would put it up there in the theorem, but it can be trouble in a more general setting. Um, uh, right, so this should give me. Three rows, two columns, two rows, two columns. Oh, right. Let's do this. Actually, no, there we go. Okay. So what happens when I multiply these numbers? What do I get? Well, this row times this column is 1. This row times this column is 0. This row times this column. Room here is 0. And then I get 0, 1, 0. And finally, I should use it. So I get that matrix in that order. What happens when I do this in the other order? Does everybody agree that the size that I get out of this one, let's see, this one is 2 by 3. This one is 3 by 2, so I should get a 2 by 2 matrix. What do I get? Looks like I get the identity matrix. Don't I? Right, the 2 by 2 identity. But notice these are different sizes. Right? So this thing, these are kind of wonky rectangular things to give me the 2 by 2. This gives me, this attempts to give me the 3 by 3 identity, but runs out of room. Right? So maybe it's not so clear then that just because I can get, let's say, A on the left by C, get the identity, does that mean that A is vertical? So this one I'm actually going to explore a little bit because everything else we sort of discussed in the class so far. So let's look at this. Let's suppose. So my goal here. Go here. CA is the identity, then A is invertible. And in fact, what's gonna happen is, C is going to be the inverse of this. Okay, suppose I'm gonna look at this, sort of like a linear transformation. I'm gonna matrix multiplex vectors. Suppose CA is IN and X is in part. So, I claim CX equals 0 and AX equals 0 only have trivial solutions. I claim that the homogeneous equation, both CX equals 0 and AX equals 0 have the trivial solution. So let me first notice if CAX equals 0, this is X, because CA is the identity. So if CA equals 0, if CAX equals 0, then X equals 0. And so that only has the trivial solution. Now let's use that. So, so let's suppose that AX equals 0. Right. Since C of AX equals 0, this means X is 0. So AX equals 0 has only because whenever you have this equation here, just apply C to it, and now you get CA. Now you get CAX equals 0, so X is 0 from that observation. So AX equals 0 has only the trivial solution. So think about the matrix A. If it's got only the trivial solution, A is an n by n, how many pivots does it have? It has to have n pivots. So because all the columns have to be linearly independent, right? So A has n pivots. But doesn't that also mean, since A is a square matrix, A is square, there's a pivot in every row. So that means always has a solution. The columns of A must span all of R n. And this is another thing we saw earlier, that when does this thing always have a solution? It always has a solution if there's a pivot in every row, which happens in this case. So now I'm going to get my second thing here. I'm going to now put in the Cx equals 0 has only the trivial solution. So suppose Cy is equal to 0. And I'm going to prove to you that y must be 0. Well, y is in Rn. So y is equal to ax for some x. Because take whatever this y is and solve that equation, because we just said you can always solve it, right? But if y is ax, this means that c ax is equal to 0. But this is the identity. So x is 0. Hence, y, which is ax, is a times 0 is 0. So now you see y only has the solution. So homogeneous Cy equals 0 has only trivial solution. So now we can pretty much finish this off now. Now suppose now let's suppose that now this is the identity, right? CA is the identity. So CA CX equals CX. You agree with that? Because this is just like one. This is like saying CX. Now, check this out. Anybody see anything I can do with that equation here? Yeah, you can sort of factor out the C, right? These are all matrices. Matrix multiplication works this way. Correct? This is C times Fred is equal to 0. What do we know about Fred? This equation only has a trivial solution. And this is plain rule of y here, right? If C times this is 0, this means this has to be 0, right? So AC x minus x 0. So ACX is equal to x for all x in Rn. So what does that mean about AC? That's right. This is a matrix and it freezes every vector. So AC is the identity. So we started with CA being the identity. Now we know AC is the identity. So that actually proves a stronger statement than what we had on. Okay, any questions? There were some key points there in the middle where I had to have the same number of pivots in the rows as the columns, and that's really why you need that here. Let me give you one last thing, how many of y'all remember inverse functions? Do you remember that from calculus? You probably did in pre-calculus, but then you probably talked about it in calculus, right? Everybody went through some kind of exercise where you had to take the derivative of the inverse tangent, right? Or the derivative of log. By the way, what's the inverse function of the natural log? Yeah, the exponential e to the x, the inverse function of tangent on the appropriate domain is the inverse tangent. Here's another one. What's the inverse of this function here? What's the inverse of this function? Cube root. That's exactly right. Inverse function is the cube root, which is basically the reflection of this around the line left, right? Notice that these are functions that undo each other, right? When you cube something and then you take the cube root back to where you started. If you take a number and you take the cube root and then you cube it back, you're back to where you started, right? That's what an inverse function is. It's a reverse here. It gets you out of where you're gone, right? One of the things about invertible matrices, remember, a big takeaway from this class is if you have a linear transformation, you can write it as a matrix, right? When that matrix is invertible, that linear transformation is invertible. It's like an invertible function. So you can do it first year, you can undo it in reverse. Right? So I'm going to do this in terms of linear transformations because we are in a linear algebra class. This will probably look familiar. A linear transformation P from Rn to Rn. By the way, well, you really need this to have the true inverse here. Is invertible. You know, there is another linear transformation. Not necessarily different, just another one. S that satisfies the following. One, S of T of X is X, right? Think cube root, right? It undoes it. And it works in both directions. By the way, let me ask you this. I said that S is another linear transformation and multiple mark, not necessarily a different one. Anybody think of an example of linear transformation T where T and S are the same thing?
Yeah.
I like that answer. That's the easiest answer. If you have the identity linear transformation, then the identity gets you back, right? Because the identity didn't want to take you anywhere in the first place, right? But there are more exotic examples. And in fact, when I write this theorem down, you might be able to write some down. There are. Let T Rn Rn be in linear transformation. With standard matrix. Okay, so in other words, Tx is Ax. So A is the way that we write the represent the linear transformation. T is an invertible transformation. If and only if. Anybody want to guess what's coming next? How can you tell if a transformation is invertible? Something about the matrix, maybe? Matrix is invertible. That's exactly right. It's exactly what I think you would hope for it to be. T is an invertible transformation if and only if A is invertible. And not only that, the inverse function S is then okay. Tell you what, I can think of just to find 4 linear transformations. T from R2 to R2 such that T is invertible and 2, the inverse and T are the same. I thought 4 each schools, I can think of some. Anybody name any? It might be best to write this in form of matrix. Okay, so you guys can figure it quick enough, so I'm gonna take the easy one. I'm gonna rip all that into town. I think another one. Zero matrix. Okay, the clever idea, zero matrix, right? Technically it didn't work though. What's wrong with it? You can't come back. That's right. Once you go to zero, baby, you ain't coming back, right? It's not invertible, right? I would think the variance on this.
With the negative resolution.
How about this? There. Because notice, this matrix is its own inverse. We multiply by itself. Basically, it's like squaring -1. I can think of 2 others. Okay. So there are 4 linear transformations that are their own inverse. I can think of another. I'm not gonna think of more as well. I can think of at least 8. But I think of another one. It's another variant on versus. what is this linear transformation do to a vector? It swaps the x and the y coordinates, right? So for example, this one. So what happens if you do it twice? You've effectively left it alone. Swap it and swap it back, right? So this is another one that's its own inverse, right? There are more. Okay, any questions on? Okay, any questions on anything else for now? All right, I don't generally do this, because I've got personal stats to maintain, but I'm gonna let you go early. I encourage you to come to my club, you got the chance. Other than that, you guys have a good weekend. Don't forget to go to 5 o'clock.
Are you gonna ask me?
Oh, I'm sorry, yeah, that's right, thank you. Actually, I changed it to 8, so you could go to that club if you wanted to. And I'll put that line in that club. Yeah, that's right, thank you.
Yeah. Yeah. I don't know. Okay. Then I just use that already. No, I don't think it's worth going all day long. I don't think it's not like.
So.
Yep.
This one.
Well, I think shower this.
This is X, Y, X. So this is rotation because the vectors stay the plane and it takes 1, 0. Goes to cosine theta sine theta. And it takes 0, 1 to minus sine theta. Whatever the state is. It's 1, 0 to x coordinate cosine, y coordinate sine. So. And this vector is minus. Notice. So basically what this does is this goes counterclockwise. Theta. And so what did I say, rotated power 4? So,
That just for two.
so, that's right, so. And then what length is it by 2?
So that's
So
just
multiply by 2.
everything by three, is that?
Everything by 2, right? Because it's basically, and if you don't like that, multiply it by this matrix here, 2 times the identity matrix, multiply it.
Okay.
So it should be radical 2 minus radical 2, radical 2, radical 2.
So generally speaking, if we're having to rotate something like along kind of clockwise, we kind of start off with that and then we just plug in whatever angle it wants us. Is that kind of how we approach that?
That's right, that's right. I just happened to, this was like something that came up in class a few times, so, this is for a particular theta. The theta we want is power 4.
Okay.
Now, when you put in part of the four though, how'd you get 1/square root two?
What do you think it is?
Is that square root two or two?
Same thing.
When you read it.
Oh, I see what you're saying.
Yeah, I don't really care about simplification.
High school was
See,
like.
1 over radical 2,
Yeah.
it's easier to write than radical 2 over 2, it's just a little lazy man.
That's
Yeah, I always hated those, I mean, I got them right when I was in high school, but I always hated them because they say simplify, and it's like, how the hell can you be more subjective than that? Right, one person's simple is somebody else's easy.
Hmm.